Welcome to Lesson 6E, Evaporation with Wind. We're going to talk about evaporation of a pure liquid with air blowing over it. Last time we talked about stagnant air. If we look at this sketch, the PJ part is the same. In the red curve, we have this partial pressure of the liquid, which is a VOC, something that's volatile. By the way, you can use this also for water to predict how much water is evaporating from a lake or something like that. But in this course, we're using it for VOCs, volatile organic compounds. The difference now is that now we have a wind blowing. So there's a wind speed, U infinity, and we're blowing over a flat surface. This would be like a puddle of liquid or a lake filled with some contaminant or something like that. Except in this example, we have a pure liquid, so this is some VOC. It's evaporating just like it did from a container, except now instead of being a container, it's just open and there's wind blowing over it. There are two what heat transfer people call films and what fluid mechanics people call boundary layers. This would be a species boundary layer, or in this case, partial pressure film or boundary layer, or a species film. And then the blue one, of course, is what we're used to in fluid mechanics, would be a velocity boundary layer or film. I'm a fluid mechanics guy, so I don't really like the word film, but that's what they do in heat transfer. And as we'll see, this will be very similar to heat transfer because of the Reynolds analogy. We're plotting partial pressure of the species. It starts at vapor pressure just like it did previously, and it goes to close to zero at infinity. We're going to define coordinates. So Z1 is at the interface, the surface of the liquid. 2 is out here at infinity from a boundary layer point of view. In other words, we're very far away from the surface. We'll call it infinity. And then, of course, NJ is the molar flux, just like it was defined previously. We'll also call this ZI in some of the notes, since it's the interface. And as always, diffusion goes from a high concentration to a low concentration. So we have the species moving with this NJ out, evaporating, just like we talked about before. The boundary conditions are at Z equals Z1, in other words, at the interface, or the liquid surface, U equal UI of the interface equals 0. That's by the no slip boundary condition. Now we're assuming that this liquid surface is not moving. In real life, the liquid would start moving a little bit as you have the air blowing over it, but we're neglecting that. We also know that PJI equal PVJ, and we're going to call this PJ1 also, since it's Z equal 1 at the interface. 1 and I are the same here. So this is the vapor pressure, and that's exactly what we did last time for stagnant air. So that part doesn't change. It's just that now we have these two boundary layers or films going on rather than just one film. And it's vapor pressure because this is a pure liquid. And some previews of coming attractions will look next time at what if you don't have a pure liquid, but you have a mixture of liquids. Then you have to deal with the mole fraction in the liquid since it's not a pure liquid. Here we still have a pure liquid xj equal 1 in the liquid itself. So that's our first boundary condition with boundary conditions on U and Pj. At Z equals Z2, which is infinity far away, we know that U goes to U infinity and Pj goes to Pj infinity. And we're going to make an approximation. This is Pj infinity out here. We're going to assume that if you go far enough away, we go to 0. In other words, we have clean air. We made the same approximation with the container up at the top of the container. Also, we have Reynolds analogy. We are going to assume turbulent flow, not laminar flow. And if you recall, for turbulent flow, we expect that the velocity, boundary layer thickness, or film thickness, as the thermodynamics and heat transfer people like to call it, is approximately the same as the species boundary layer thickness, which is approximately the same as the thermal boundary layer thickness. Why? Because everything's happening at the same rate, whether you're diffusing momentum, species, or heat. The Reynolds analogy also says that the species diffusion rate is approximately the same as the momentum diffusion rate is approximately the same as the energy or heat diffusion rate. All of these occur at the same rate, roughly, because any property is being swept up by these big eddies. So if you have some hot molecule or you have some species, this VOC rather than air, it's going to be swept up very rapidly through the boundary layer because it's turbulent.
Sir, aren't those eddies going the wrong way since the flow is faster on top?
Yes, Mr. Kirchhoff, you're correct. I'm actually drawing these the wrong direction. The predominant eddies will be clockwise. The usefulness of this Reynolds analogy is that we will use heat transfer equations to approximate species transfer. So a lot of this is going to look like heat transfer. I'm assuming that some of you have had the heat transfer course and some of you may not have had it yet. Don't worry if you haven't had it yet. I'll say it this way, if you've had heat transfer already, you'll be helped by it a little bit here. If you haven't, then when you take it, you will be helped a little bit then by what you're learning here. So either way, it's good to see some repetition like this. Qualitatively, it turns out that the evaporation rate goes up as U infinity goes up. If the wind blows harder, you expect the liquid to evaporate faster. That's common sense, and we know that from experience. Just as heat transfer rate goes up as U infinity goes up. I'll use this symbol to mean analogous to. These are analogous because of the Reynolds analogy. Quantitatively, same as before, NJ is the molar flux. It's exactly the same as before. NJ equal kg, this mass transfer coefficient, times pji minus pj infinity in this case, or we've saw it as pj1 minus pj2. This is the same thing. It's exactly the same equation we had previously, where kg is the mass transfer coefficient, just like it was before, except now kg is different. See kg equation. The next page will show you how to do that. Once you have that, then we calculate the mass flow rate or the source strength. M dot J is the same equation as stagnant. Namely, M dot J was NJ times capital MJ, molecular weight, times AJ, the area above this surface now. Before, we had a container with liquid in it, and the A was this cross-sectional area above the liquid. It's the area of the container. Now we have some kind of a puddle along the ground, and the area is this surface area of the liquid puddle. There's a lot of equations here, and I don't want to write them all down, so I typed all this up. See all the equations on the equation sheet, and I've copied those here for your convenience. Evaporation, pure liquid into moving air. Yj plus Ya has to be 1 since there's only 2 species. Air, A and J is the species. Z1 is the liquid surface, Z2 is Z infinity. Free stream above the boundary layer, far away. Nj is, I just gave you that. Here's the more ugly looking Kg than we had previously. So we're going to have to define all these things. Reynolds number, Schmidt number, we already know what those are. Prandtl number, Nusselt number, what in the world? That's a heat transfer thing. Here's a heat transfer coefficient, and that's exactly right. This is the Reynolds analogy. We're going to use the same equations we have for flow over some kind of a heated plate. If this was a heated plate and we have a boundary layer growing over it, we'll use the exact same equations we have for heat transfer, and we're going to apply them to species instead through the Reynolds analogy. The Nusselt number depends on geometry, Reynolds number, Prandtl number, etc. And then we have a PAM, which is defined exactly as previously, except I have an infinity instead of a 2. This is for the air, so make sure you don't make that mistake. That's for the air, not the species. So you're always going to be converting using either Yj plus Ya equal 1, or if you want to do it in terms of pressures, remember Dalton's law. Sigma of Pj has to equal the total P. So if you have one, you can get the other. This is all best illustrated by example. Instead of writing all this out, I just copied and pasted from the textbook, and I will walk you through this. We're estimating the evaporation rate of a pure liquid. When we wrote this book, we tried to make things as real to life as possible. So suppose you have ethyl mercaptan. It's a liquid. It has a skunk-like odor. PEL is very small, 0.5 ppm, so this is bad stuff. You have a 55-gallon drum. A leak develops. A circular pool of this liquid 10 meters in diameter develops. The wind is 3 meters per second. We want to estimate the evaporation rate. You can call this a source strength m dot evaporation J in units of kilograms per hour. We're using kilograms instead of milligrams because we're going to find this is actually quite a large amount of evaporation. And then once you know that, you can start calculating how long it'll take for this stuff to totally evaporate. Solution, we assume that the partial pressure of the contaminant in the liquid-gas interface is the vapor pressure, like I said, PVJ. So we look at Appendix A8 to find that. In this equation, we have an L. That's a characteristic length. And so here, L equal D equal diameter of the puddle. If you had a different problem, it might be a different characteristic length, depending on the geometry. The temperature is given. Total pressure is the standard atmosphere. So this is not SATP. We look up these guys in the tables or the NIOSH pocket guide, and we find the molecular weight, the binary diffusion coefficient. By the way, I have JA here. DAJ and DJA are the same because it's a binary diffusion coefficient between air and species J. We know 400 millimeters. Plug that into PIJ. To get PAJ, we look up the kinematic viscosity of air, Prandtl number, and U infinity is given. So we use the following equations. First, I calculate PAM. That's why I had to calculate PAJ. I'm assuming that PA2 equal PA infinity equal P itself. So we have pure air out there. That's clean air. Then we get PAM. You can do this either in millimeters of mercury or in kPa. You just have to be careful that you keep your units consistent. Reynolds number, we calculate. And now you go to table 4.3. I copied and pasted a screenshot here for your convenience. So we look in the book or look here and you see these definitions for Nusselt number, etc. What we're really interested in is whether it's laminar or turbulent. This one is definitely turbulent. Our Reynolds number is 1.9 roughly times 10 to the 6, so that's in this range. And our Prandtl number is 0.707, which is in this range. So we want to use this equation. And now it's just a matter of plugging in. So we plug in that equation with the given Prandtl number. Prandtl number, Nusselt number, Reynolds number are all non-dimensional. There's no units here. Schmidt number, also non-dimensional. And then we calculate kg from that big ugly equation. Plug in all the numbers. The units turn out to be kilomole per meter squared second kilopascals. So we have kg. Once we have kg, we can use this equation to get nj. Plug in everything, we get nj is 1.02 times 10 to the minus 4 kilomole per meter squared second. And then finally, the evaporation rate, m dot evaporation J is nj mj times A. Just a reminder that this up here is of the air, not the species. Here's the part that's a little bit trickier. These PJs are of the species, not the air. So a common mistake that I've seen on exams and homework and stuff is you're used to dealing with PAs up here because you're doing this log mean partial pressure ratio up here in terms of the air. But then when you get to NJ, it's in terms of the species. So as long as you keep your variables straight, you shouldn't have a problem. So finally, we plug everything in, do some unit conversions. This is the area here, area of a circle, since it's a puddle, a circular area on a ground like this with the wind blowing like this. So this is the area, pi over 4d squared, and plug everything in. And to 2 digits, which is certainly the best you're going to do with this kind of a problem, I get 1,800 kilograms per hour. I would highly recommend, before I stop here, that you go through all these calculations. You can do them by hand if you want. I would recommend that you put them in Excel or MATLAB or something. Make sure you get all my numbers. I don't think there's any mistakes here. If you can get my numbers here, you'll be fine for the homework and quizzes. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.